Hello, space enthusiasts and curious minds. Today, we're embarking on a cosmic journey to the edge of our solar system with the latest marvel from the James Webb Telescope. Our solar system. Pluto was the first Kuiper Belt object identified, and for approximately 60 years, no additional discoveries were made within this region. However, on November 2, 2015, the world was introduced to an unprecedented view of a Kuiper Belt object, marking one of the most extraordinary space photographs ever released to the public. This perspective has recently been surpassed by the James Webb Space Telescope, which has captured the sharpest image of the Kuiper Belt to date, revealing aspects that have taken everyone by surprise. Situated in the outer reaches of the solar system, the Kuiper Belt encompasses a cold, donut-shaped area beyond Neptune's orbit, which is the eighth planet from the Sun. Initially, the belt's shape captured the interest of astronomers, but it soon became apparent that its significance extended far beyond that, offering profound insights into our planet and the solar system at large. Named after the astronomer Gerard Kuiper, the Kuiper Belt honors his mid-20th century contributions that paved the way for our current understanding of this distant region. Although Kuiper speculated about the existence of objects beyond Pluto in a 1951 scientific paper, he was not the discoverer of the belt itself. Gerard Kuiper's early work primarily explored the possibility of objects existing beyond Pluto, though it didn't offer specific predictions about the characteristics or layout of these objects. Initially, Pluto was seen as a key element of the Kuiper Belt, but it's now recognized that the inner boundary of the belt is actually defined by Neptune's orbit. Neptune's gravitational forces have significantly influenced the structure and dynamics of the Kuiper Belt. While Kuiper's initial predictions did not precisely match later observations within the belt, his foundational ideas and contributions remain highly regarded in the astronomical community. The concept of the Kuiper Belt, along with its association with objects beyond Pluto, became closely tied to Gerard Kuiper. In 1930, Clyde Tombaugh discovered Pluto, marking it as the first known object in what is now referred to as the Kuiper Belt. At the time of its discovery, the understanding of the solar system's outer region was quite limited, and the existence of a vast population of icy bodies beyond Neptune was unforeseen. The conventional view of the solar system included the inner rocky planets, the gas giants, and Pluto as the outermost icy body. Despite Pluto's elliptical and inclined orbit, its discovery led scientists at the time to classify it as a standalone planet. It wasn't until 62 years later, in 1992, that a second object within the Kuiper Belt was identified, revealing that Pluto was not solitary but part of a larger collection of outer solar system bodies. This and subsequent discoveries of numerous Kuiper Belt objects, KBOs, confirmed the presence of the Kuiper Belt, a region filled with a diverse array of icy worlds beyond Neptune. Pluto holds a unique place in astronomical history, originally classified as the ninth planet, a status it maintained for several decades. However, as our knowledge of the Kuiper Belt expanded and more KBOs were discovered, some even larger than Pluto, the International Astronomical Union, IAU, revised the definition of a planet in 2006. As a result, Pluto was reclassified as a dwarf planet. Nonetheless, Pluto remains a significant discovery in our solar system, as it spurred further exploration into the Kuiper Belt. This distinctive region is considered an extension of our solar system, part of our cosmic neighborhood, and influenced by the gravitational forces of the Sun, alongside the 8 major planets, including Neptune. While the inner solar system is dominated by rocky planets and the asteroid belt, the Kuiper Belt expands the solar system's frontier into the outer reaches. This region is markedly different from the inner solar system, housing a plethora of icy objects, including dwarf planets, asteroids, and comets. NASA suggests that the Kuiper Belt's contents are remnants from the solar system's infancy, approximately 4.6 billion years ago, preserving the conditions and materials of that era. This makes the Kuiper Belt is significantly vaster. While the asteroid belt is relatively dense, and contains numerous small to medium-sized objects, the Kuiper Belt encompasses a more expansive and remote area. The mass of the Kuiper Belt is estimated to be substantial, highlighting its importance in the solar system structure and evolution. The mass of the Kuiper Belt is estimated to be up to 100 times greater than that of the asteroid belt, showcasing its significant material wealth in terms of both the number of objects it houses and their collective mass. This vast difference partly explains why its discovery took an extended period, underscoring the notion that the duration of discovery does not diminish its importance to the solar system. The Kuiper Belt is a rich tapestry of celestial bodies, including dwarf planets such as Pluto, Haumea, and Eris. Pluto, identified by Clyde Tombaugh in 1930 and once deemed the ninth planet, saw its status altered to that of a dwarf planet in 2006, following the International Astronomical Union's revision of planetary definitions. Pluto, measuring roughly 2,377 kilometers in diameter, shares the Kuiper Belt with other notable dwarf planets, contributing significantly to our understanding of this distant domain. The exploration of Pluto has paved the way for further insights into the Kuiper Belt. The discovery of Haumea in 2004 by Mike Brown and his team, notable for its elongated shape, possibly due to rapid rotation and measuring about 1,600 kilometers in diameter, enriches the diversity of the Kuiper Belt. Similarly, the discovery of Makemake by Mike Brown's team in 2005 adds to our knowledge with its unique characteristics, further highlighting the intriguing nature of Kuiper Belt objects. These dwarf planets are instrumental in shedding light on the composition and evolution of the Kuiper Belt, as well as its significance within the grand narrative of the solar system's history. Without these discoveries, our understanding of this region would be significantly less developed. There's a common misconception that confuses the Kuiper Belt with the Oort cloud. However, the two are quite distinct. The Kuiper Belt is more densely populated with objects and is known as a source of short-period comets, which have relatively brief orbital periods. In contrast, the Oort cloud is a much more distant and spherical region that surrounds the solar system. It is thought to stretch from about 2,000 astronomical units from the Sun, serving as a distant boundary of our solar system's influence. The Oort cloud is believed to extend from about 2,000 to potentially 200,000 astronomical units from the Sun. This distant cloud is made up of icy bodies, often likened to dirty snowballs, and is theorized to be the origin of long-period comets. These comets have highly elliptical orbits that bring them closer to the Sun. While the Kuiper Belt and the Oort cloud occupy different locations and have distinct shapes, they share the characteristic of being reservoirs for icy bodies. Both regions are considered potential sources of comets, celestial objects made of ice, dust, and volatile compounds that become visible with a glowing coma in tail as they approach the Sun and interact with the solar wind. Hence, the confusion between the two is somewhat understandable, though it remains crucial to recognize their differences. One aspect of the Kuiper Belt that has astonished scientists is the current amount of material, which may only represent a small fraction of its original mass. The remnants we observe today are just that, with the majority of the original material having dissipated over time. This loss was not a random occurrence. The NICE model, a theoretical construct, proposes a series of significant orbital adjustments in the outer solar system. This model involves the movement and interaction of celestial bodies, shaping the current structure and composition of the Kuiper Belt and influencing the broader dynamics of the solar system. The NICE model addresses the orbital history of the four giant planets Jupiter, Saturn, Uranus, and Neptune, suggesting that their current positions in the solar system were not always as they are now. This model proposes that these planets underwent a period of dynamic orbital evolution, with interactions among them leading to significant alterations in their orbits. As a result of these orbital shifts among the giant planets, the NICE model theorizes that a considerable amount of material from the Kuiper Belt, initially estimated to be 7 to 10 times the mass of Earth, might have been lost. The gravitational forces and orbital changes of these giant planets are thought to have scattered material from the Kuiper Belt, ejecting some of it from the solar system or transferring it to other regions. This has led to a gradual erosion of the Kuiper Belt, where collisions between objects within the belt generate fragments, contributing to the formation of smaller Kuiper Belt objects. Some of these smaller bodies may turn into comets, while others do not. Non-cometary material gets ground down, with the dust generated from these collisions potentially being expelled from the solar system by the solar wind. The total mass of material currently in the Kuiper Belt is estimated to reflect this process of slow attrition and transformation. The current estimated mass of the Kuiper Belt is thought to be no more than about 10% of Earth's mass. While this may appear small at first glance, it's still significant, especially considering the number of Kuiper Belt objects, KBOs, found to have their own moons. These mass orbit around a common center of mass, often called their barycenter. These binary pairs can exhibit a range of orbital characteristics, including some that physically touch, forming a unique peanut shape. Such configurations are known as contact binaries, where the two components are in physical contact and their mutual gravitational attraction molds them into this unique formation. The existence of these features within the Kuiper Belt wasn't always well understood. NASA's Pioneer 10 mission, launched on March 2, 1972, was among the initial endeavors to approach this distant region. As a groundbreaking spacecraft tasked with the exploration of Jupiter and its environment, Pioneer 10 was equipped with scientific instruments designed to study Jupiter's atmosphere, magnetic field, and more, paving the way for future explorations that would further our understanding of the Kuiper Belt and its myriad of objects. Pioneer 10 carved its place in history as the inaugural spacecraft to traverse the asteroid belt, setting a precedent for space exploration. In 1983, it further distinguished itself by becoming the first spacecraft to enter the Kuiper Belt region. Despite its entry, Pioneer 10 did not conduct close-up studies of any icy worlds within the Kuiper Belt, as Pluto was the only such body known at the time of its launch. The mission's primary focus was on Jupiter, from which it transmitted invaluable data back to Earth. Pioneer 10's trajectory and durability enabled it to venture far beyond the orbits of the known planets, enhancing our knowledge of the solar system's outer limits and barely crossing into the Kuiper Belt. This mission laid the groundwork for future explorations of this distant and fascinating region. Subsequent missions, like Voyager 2 and Cassini, significantly broadened our comprehension of the outer solar system. Voyager 2's visit to Neptune's moon, Triton, in 1989, and Cassini's investigation of Saturn's moon Phoebe in 2004 offered crucial insights into these celestial bodies. Some of these moons are thought to have originated in the Kuiper Belt, later being captured by the gravitational pull of their respective planets, a concept that remains surprising to many. These exploratory efforts marked the beginning of an extensive quest for knowledge in this region, indicating that much more information about the Kuiper Belt and its contents awaits discovery. The New Horizons spacecraft etched its name in history by executing the first ever flyby of Pluto in 2015. During this mission, it managed to capture images of a Kuiper Belt object designated as 1994 drone. This object, spanning 90 miles in width, was observed from a distance of 170 million miles, shedding light on the composition and characteristics of Kuiper Belt objects. In 2014, the Hubble Space Telescope played a pivotal role by identifying 3 KBOs as potential candidates for New Horizons' Pluto mission. Additionally, Hubble discovered 2 icy bodies within the Kuiper Belt at the edge of our solar system. These discoveries led an ASA to greenlight an expanded search for Kuiper Belt objects, aiming to find a new target for New Horizons to study closely after its encounter with Pluto. The 2 objects identified from this search, known as 11,113 Y and 72Z9F, are situated roughly 4 billion miles from Earth. The Hubble Space Telescope's involvement in exploring the Kuiper Belt dates back to 2003, illustrating its long-standing contribution to our understanding of these distant celestial bodies. The Kuiper Belt object, designated as 2000 F53, first spotted from Hawaii in March 2000, significantly influenced the Hubble Space Telescope's targeting strategy. This object's discovery paved the way for Hubble to identify 3 additional Kuiper Belt members, which are notably faint, being up to 100 times dimmer than 2053. Their low brightness makes them undetectable to the naked eye, requiring astronomers to employ computer analysis for their identification. The advanced camera for surveys aboard Hubble successfully tracked one of these objects on January 26, 2013, hinting at the vastness of what was yet to be discovered. The entrance of the James Webb Space Telescope into the field dramatically enhanced our ability to explore such regions. With its advanced technology, the James Webb Space Telescope has significantly broadened the scope for observation and analysis. This cutting-edge observatory is particularly adept at studying the cosmos, including the Kuiper Belt, due to its utilization of infrared technology. Since all objects with a temperature above absolute zero emit infrared radiation, the intensity and distribution of this radiation provide valuable information about their characteristics, making the James Webb Space Telescope an indispensable tool for understanding the complexities of the Kuiper Belt and beyond. In the cold expanse of the Kuiper Belt, where temperatures plummet, the emitted infrared radiation manifests as longer wavelengths. This characteristic enables telescopes, like the James Webb Space Telescope, to more effectively collect data about these distant objects. Different materials emit or absorb infrared light in unique patterns, known as spectral signatures, which are distinct for each type of material in the infrared spectrum. When astronomers examine a Kuiper Belt object using infrared light, they analyze the specific wavelengths of infrared radiation that are either emitted or absorbed by the object. These spectral features reveal the object's composition, allowing astronomers to detect the presence of various chemical compounds and minerals on its surface. For instance, substances such as water ice, methane, and ammonia exhibit unique infrared signatures, enabling scientists to deduce the composition of celestial bodies without direct visible light observations. Moreover, infrared radiation has the advantage of penetrating through dust and gas more efficiently than visible light. This capability is particularly useful in the Kuiper Belt, which may feature environments with dust or thin atmospheres. Thus, infrared observations provide a powerful tool for uncovering the secrets of these distant objects, beyond the reach of traditional visible light techniques. Infrared observations offer enhanced clarity in viewing celestial bodies, a boon for examining the surfaces and characteristics of Kuiper Belt objects by minimizing the effects of atmospheric disturbances and blockages. The Kuiper Belt, located at the solar system's outer edge, is populated by tens of thousands of icy bodies, which are essentially the preserved remnants from the solar system's formation. Infrared technology excels in studying these cooler objects, as visible light observations may not adequately reveal their properties. However, the James Webb Space Telescope, JWST, also plays a crucial role in these studies. The JWST's large primary mirror is instrumental in amplifying its observational power. The primary purpose of a telescope's mirror is to gather and focus light from celestial bodies. With a diameter of 21 feet, the JWST's mirror offers a vast surface area to capture and concentrate light, significantly boosting its ability to collect faint signals from distant objects. This makes the JWST exceptionally suited for observing the Kuiper Belt, where many objects are either faint, distant, or both, providing a comprehensive view of this distant and dimly lit region of our solar system. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, You will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and as sessions with experts. Your membership will grant you the chance to participate in live Q and a sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blesovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.